Le Chatelier's principle is when we disturb an established equilibrium by changing the volume, the temperature, or the concentration. In this one page of notes, I will be only focusing on volume changes. I have a separate video for concentrations being changed and another one for temperatures being changed. This is part of Unit 7 in AP Chemistry on equilibrium, but it could be part of your college level course in general chemistry when you get to the equilibrium topic. All right, this is kind of the definition or description of what happens when we have the volume changing. A couple important things you need to note are that we have to have gases in our reactions, and we have K values, our equilibrium constant values, again staying the same, similar to how we had that when we had the concentration changing. The other thing that will be helpful is to think about PV-nRT and how that's kind of like in play. And also some particle views that we'll want to count out the actual particles to see how it proves that we shift left or shift right when we have these volume changes. All right, so let's take a look at decreasing the volume. Make sure you sort of pay attention to that A are the red, B are the orange, and then our products are these AB cubed. And to count how many are actually in each of these different containers when the changes are happening. All right, so let's zoom in and just take a little look at the first one and do a nice slow attempt at this one. Then we'll go a little faster when we get to the next change. So we have 1, 2, 3, 4 of the B squared, and then are the diatomic Bs, and then these are the As, and there's 2 of those, and then we have 2 of the products here, and in the initial volume, okay? So then what we're gonna do is we're gonna have the new volume be less, okay? Maybe it's a piston and the valve gets pushed down, but take a look, we have now 1, 2, 3, 4 of the products, and now only 1 of each of these left. And kind of look at how that stoichiometric ratio makes sense. I don't want this video to be too long, so I'm just gonna focus on it from a PV equals nRT kind of aspect. So what's going to happen is if our volume decreases, what the equilibrium will do with that disturbance is if the volume goes down, initially the pressure is going to go up, but what the reaction will do to try to avoid that pressure increase is it will drop the amount of moles of particles, and so it's going to shift to the side that has less moles of gaseous particles. So if you look at our reaction that we have here, we have 4 moles on this side, and that's because we have 1 and 3. Add that up, that's 4. And they're all gases, and then we only have 2 moles on this side. So what'll happen is the equilibrium will force the particles to create fewer number of moles of gases to adjust for that change that occurred in the reaction. All right, so here's a summary that I have sort of pre-written, is that when we have an established equilibrium and it has gases and the volume is decreased, the pressure will momentarily increase, and as a result, we will have a shift to the side. I'm just going to zoom in, I lost my T on this one. It'll shift to the side with fewer moles, so you have to look at your reaction. In this case, that's our product side, to keep the pressure value adjusted so that our K value will stay the same. All right, so let's look at another example, and I probably won't count the particles quite as much. And I do have the Kp values written off to the side in case that's something that you need a little extra practice on for writing the equilibrium expression. All right, so if we look at this one, our volume is going to start out here, and then we're going to let it get bigger in our second picture. So again, just to kind of use PV-nRT, so we have this initial set of conditions, and then our new set of conditions, what happens is the volume goes up. Okay, so I'm just going to kind of put an arrow underneath. The volume goes up, and if you count the particles, I'm not going to count them this time. You can count them by pausing the video. But you'll notice that we have more moles of gas show up, and what happens is some of these product particles are now being consumed to create the reactants. Again, remember this side had 4 moles, and this side had 2 moles. So what'll happen is it'll, shift or favor the side that has, in this case, more moles of gas. And that's because for a moment, the pressure goes down. And so what the equilibrium reaction does is it creates more particles or more moles of particles to adjust for that change. And again, we're trying to keep the K value the same for this also. All right, there are two more possibilities that you might see that involve moles of gases. The next one, I don't even want to show you what happens. I want you just to count the number of moles of gases. And you're going to notice that for this one, be careful, there's a solid in there. So this one has the same moles on both sides. So if we were to write the equilibrium expression, the other thing that's important is we would have the AB squared, and then we would have the pressure of A squared. But since they both are the same number, if we tried to change the volume, it wouldn't have any effect because both sides have the same number. So don't kind of fall into that trap. First off, remember that solids do not go into the equilibrium expression. And secondly, there'd be no shift in this reaction because they have equal moles on each side. All right, last but not least is what about an inert gas? This is pretty common that you'll add an inert gas to a reaction. The first thing, again, look back at this K equilibrium expression. If I add helium, so let's say we add helium, let me just put that in, let's just do purple. So let's say I add the element helium in, which is an inert gas. It's not in the Kp, okay? So because it's not in the Kp, the easiest way to explain it is it can't affect the equilibrium constant. The other thing you could do is say that because it's an inert gas, it'll affect both sides the same. So adding an inert gas, such as helium, will not change the K value. And even though the pressure, because there are more gaseous particles, might go up, it goes up, or basically both sides. And this doesn't have to be equal moles. These could be different moles. This would still have the same effect in that the gases, they remain the same on both sides, the partial pressures. So don't try to get talked into an inert gas being added to a reaction. It does not affect or does not cause a shift or a disturbance in the equilibrium at all. And it doesn't matter if the moles are the same on both sides or not, the inert gas has no effect. The other thing is a catalyst. I'm just going to add that in here in one last color here. Let's use maybe, we'll just do gray here. The other thing is be careful if we add a catalyst. A catalyst also is not going to affect the equilibrium constant. You just will end up having the reaction reach equilibrium faster. So I'm just going to write that kind of at the bottom here. If we add a catalyst, where the equilibrium, so the equilibrium will reach its value, whatever value it's going for. The equilibrium will just be reached as K value, okay? So whatever the K value is, just faster, not more. It's not like we're going to make any more products or less products. There's not a shift. It just reaches its equilibrium position that it's going for at a quicker time frame, okay? So that's the last thing I wanted to throw into this, that, you know, catalysts are not part of the Chatelier. Just volume, temperature, and concentration. And again, I have videos that you can watch for those. Just a quick review one more time. If we decrease the volume, I'm just going to zoom in. If we decrease the volume, it's going to favor the side that has fewer moles of gas. Just count which side has fewer moles of gas. If we increase the volume, it's going to favor the side with more moles of gas to create, again, an increase in that pressure that momentarily would drop. And then if we have equal moles, there's no effect on that equilibrium at all. There's no disturbance. Same with an inert gas, and also same with a catalyst. You're going to have no effect on the disturbance of that equilibrium. All right, well, I hope this helped you solve your Le Chatelier problems. And again, remember I have a video on concentration and another one on temperature changes for the Le Chatelier principle.